So today, gyroscopic motion. This is the last of the three ways we're going to use this equation. So we have our sum of the moments vector, and this is the moments on a body, is going to be equal to I, the matrix, times any acceleration vector, plus any rotation of our angular momentum vector here, which is going to be, I'm going to draw this differently, which is going to be our I matrix times our omega, and then we're going to rotate it by this. So here's our general equation, and now in this case, we're thinking about gyroscopes, and so gyroscopes are special in a couple ways. I'm going to just kind of draw our basic gyroscope here. And they can be lots of different shapes. Let's kind of try to draw a symmetric one here. But so gyroscopes are special because they have some spin p in the z-axis, right? So this is going to be the primary spin axis. So maybe it's moving around a little bit, but it's moving pretty fast in p. And then also the I matrix is special in that I x, and let's say this is the x direction, is going to equal I y y, which is not necessarily going to equal 0. So and then y would be, let's see, x, y, z. So y would be out of the board here. And because this is a spinning disk object, then that's another way of saying that these two are equal, because it's symmetric, rotationally symmetric about the z-axis. So these two are going to be not equal to 0, but usually equal to each other. But we're going to also be able to say that because of that symmetry, all the off-diagonal terms are equal to 0. So we don't have any of these terms. Okay, and so now what makes this interesting as a gyroscope, not just a regular spinning body in 2D, is that there is some slow rotation. And that's going to be this big omega. And it's much, much smaller than p. And we're going to, just for our convenience, we're going to call it equal to the rate of change of this angle here. So if we have some angle here. So it's going to be rotating in this direction, and we're going to, for now, we'll kind of define that in the j direction. So out of the board. So it's turning this way, so it's out of the board. Okay, so given these assumptions, now we can make a simpler equation from this main source equation. All right, so I'm going to erase all of that. My board is kind of small. So here we're going to have then our sum of the moments in all the directions is going to be, oh, and then one other final thing, the final assumption is that there's no rate of change in our big spin vector p. So we're going to neglect this term, because we're going to assume that whatever our spinning thing, it's spinning at some high rate. We're going to neglect the friction during whatever operations we're doing, so it's going to keep spinning at that same rate. So now that just leaves us with 0, big omega, 0, crossed with, and now because our I matrix looks like this, I, x, x, I, y, y, I, z, z. Give myself a tiny bit more room here. 0, 0, p. So now when we do this matrix multiplication, the only term we end up with is here. So now we just have our sum of the moments equals big omega in the j crossed with I, z, z times p in the k which you can already see J cross K is going to be in the I direction. So we've got omega I, Z, Z, P in the I direction. And this is where this is a little bit strange when you look at this diagram here, because this is our X direction. So when you rotate this axis of the spin axis Z, when you rotate it this direction, it actually doesn't create a moment in this direction, which you might kind of guess. It's actually creating a moment here in this direction. So you put your thumb along the X axis here, and that is the direction of the moment. Positive I that would cause that rotation. Okay, so, and then if it, in this case, I kind of drew all the axes perpendicular, but you can still use this equation if this big omega vector isn't perpendicular. You just end up with sum of the moments equals I. And now when we're talking about gyroscopes, sometimes we drop the subscript, so it's just this term. It's not I the matrix, it's just the important I, which is I the ZZ. But I'm going to put it in here just to be clear. IZZ omega vector crossed with the P vector. All right, so this is our simple moment equation, and it's useful in a lot of different problems. Let's do one example that I think is cool of a bus. So imagine there's this bus here, and it's driven by a flywheel for energy, kinetic energy instead of gasoline. So that's this problem here. There's a bus, it's driven by some flywheel, and it starts to go over a little hill. So that's this kind of ramp here. And as it goes up this ramp, it changes the forces on the tires. So which tires get more weight and which tires get less. So we'll draw this is our spin axis direction. Okay, so it's spinning in this direction. So you can imagine that our angular velocity is I omega, and that's going to be pointing up if we curl our fingers around this. And so this is the forward direction of the bus. Okay, and now when this bus tips, our I omega matrix is now, or our angular momentum vector here is now going to be pointing still perpendicular to the bus, but in this direction here. So it will have moved, it will have changed in this direction. If we drew like the original angular momentum vector here, and then we'd have some new angular momentum vector here. And so the change would be in this direction, right? So if we now think about that, then that means that the moment applied to the flywheel, the sum of the moments applied to the flywheel have to be in the change of momentum direction this way. So that means that the moment applied to the bus is going to be this way, the opposite of that. So up along this axis of the bus, right? This is going to be the sum of the moments applied by wheel on bus, because it has to be opposite from the sum of the moments applied by the bus on the wheel, which we know has to be equal to the rate of change of momentum. So, okay, so now we can think about this. So the sum of the moments is going to be in this direction. And we can draw then our bus kind of like this. Now we're kind of looking at the tires from the back, right? And so here's the flywheel at the center, and this is the rear of the bus. And so the moment is going to be pointing then into the board like this. So that moment that's this moment applied by the wheel on the bus is going to be in this direction, which means that there's going to be now more force on this tire. So it's going to want to kind of rock the bus. This is exaggerated, but ever so slightly in this direction. And if you're on the bus, this is going to be the left side where the driver is in the US, left, and this is going to be, if you're on the bus facing forward, like we are here, here's the rear, right? Then there's going to be more force on the right tire, which you might not expect if you don't do some of these gyroscopic moment equations.